Bismillahirrahmanirrahim, dear students, grade 12, lecture number 53, grade 12, and we already started phenols. And in the last lecture, lecture number 52, we done the acidity of the phenol. Acidity of the phenol in the last lecture we done. So in the acidity of phenol, we discuss the different resonance structure of phenol, how the pi electrons are going to be shifted or circulated inside the ring. Then we compare the acidity of the alcohols with phenol. And we concluded in the previous lecture that phenol is more acidic than alcohol. Phenol is more acidic than alcohol. Now we compare, according to your reduced syllabus, we compare here that comparison of acidity number 2. This is number 2. Of acidity of phenol and carboxylic acid. So now we are going to compare the acidity of phenol with carboxylic acid. So you can see here reactivity of phenol, reaction of alcohols, nomenclature of phenol, structure, physical properties, comparison of acidity of phenol, alcohol and carboxylic acid. So dear students, you can see the resonant structures of carboxylic acid. Resonant structures. Resonant structure of carboxylic acid. So this is the alkyl group attached with the carboxylic acid. This is the ketone group and this is the alcohol group. The whole we call carboxylic acid. So this is the structure number 1. And it's going to be resonate. How it is going to be resonate? When you will put double bond here. So when we are going to put here double bond. So when I put double bond here, so this double bond is going to be removed. No more double bond is there because valency of carbon is 4, 1, 2, 3 and 4. Don't put double bond, it is going to be vanished. So when the double bond you put between the carbon and oxygen with the hydrogen and you remove the double bond from the oxygen, so the valency of both is not going to be satisfied here. So that is why the negative charge is created between the carbon and oxygen. This is a negative charge on oxygen, and because the oxidation number of exceed, so that is why positive charge is created here. So this is the shifting of double bonds. So there are two resonating structures here. So there is the involved charge separation. Involving charge separation. So this is the there are two structures here. Now when we know that carboxylic acid is the weak acid, carboxylic acid is a weak acid, so a little of the carboxylic acid is going to be ionized. So I put ionization of the carboxylic acid in water. So it is going to be ionized little if you give carboxylate ions plus hydrogen ions in aqueous solution. Carboxylate ions and the hydrogen ions in aqueous solution. So this is a carboxylate ion, this is a hydrogen ion, this is the ionization. So now we are going to make the resonant structure of this carboxylate ion. So this is the R, double bond O, lone pairs, oxygen. This is the carboxylate ion. This is the structure of carboxylate ion, and this one is the third number structure. This is the whole carboxylic acid. This is the resonance of carboxylic acid, second structure. And this one is a carboxylate ion. Carboxylate ion, this is the third structure. And when we are going to resonating it, just you are, this is good. Here between carbon and oxygen, here you are putting double covalent bond. And here carbon and oxygen, there is a single bond, and double bond I shift here. So there is one thing very here written. Now the resonant structure of 1 and 2 of carboxylic acid are not equivalent, non-equivalent. Great difference. These structures, resonating structures of carboxylic acid are non-equivalent. They have no equivalency because carbon and oxygen double bond, carbon oxygen hydroxyl group is single covalent bond, valence is fully satisfied. So when I shift double bond here, so charge is going to be involved here. Difference both. So these are non-resonating structure 1 and 2, and hence much less stable than the resonating equivalent structures. So these 1 and 2 show instability. They show instability than the equivalent resonant structure of 3 and 4. So this you can see how they are more equivalent, they are equivalent. These are the equivalent structures. This is a carbon. See, only difference is that this C double bond O before here and this carbon oxygen here are negative charge. So there is no difference like differences. Only the position of the carbonyl group is going to be changed and the carbon oxygen is going to be. So there is no difference. There is no much difference between them. So these structure number 3 and structure number 4 are equivalent structures. Number 1 and 2 are non-equivalent structures, hence much less stable than the equivalent structures 3 and 4. These are much more stable, these are less stable of carboxylate ion. Thus, carboxylic acids have tendency undergo ionize to form more stable carboxylate ions by giving protons. So this shows that when the proton is there, before ionization, the 1 and 2 resonating structures are unstable. When carboxylic acid gives proton to make carboxylate ion, then if we draw the two resonance structures, they are much equivalent. They show stable. It means that carboxylate ions are more stable than carboxylic acid. That is why the ionization form of the carboxylic acid is much more stable and than proton. So due to this reason, when you are going to compare the resonant structure of phenol, the carboxylic acid is much more acidic than phenol. So here we compare the phenol structure and carboxylic acid structure. Now this is the carboxylate, so I must compare with the phenolate ion. So now I am going to writing here phenolate ion. Now let us compare the acidic strength of carboxylic acid and phenol. The resonant structure of phenolate ion are not equivalent as shown. So now you understand that these two carboxylate ions are much more equivalent and show more stability. Now I am going to draw the structure of phenolate ions. Phenolate ions now, and he said that these are not equivalent, structures of phenolate ions. So when hydrogen is removed from phenol, you will get phenolate ion. So this is the one structure of phenolate ion. This is the first structure, or you can say before you done 4, this is number 5. Structure number 5 is one. Now structure number 6. Only you remove hydrogen. So now starting bond from here, the same like this one. Before the bond was here, now I shifted here, both are same. This is number 6. Number 7. Number 7. Now put double bond here. The valency of the oxygen is going to be complete, and this bond is no more here. So the positive charge is going to be created. There is no bond between this carbon and like this. Like this one. Same as a phenol. This is number 7. Okay, number 8. Resonant structure number 8. Just shift the charge. Now charge will be here. The negative positive charge is going to be created. Charge will be created here, and this bond shifted to here. Like this. So this is the structure number 8. And structure number 9. this charge is going to be shifted here, and this bond is reversed back like this one, and this is a resonance structure number 9. So dear students, we concluded that structure number 3 and 4 for the carboxylate ion is much more stable than the resonance structure of the phenol. The resonating structure of phenols or ion are not equivalent. They are not unequal. They doesn't show resemblance because double bond is here, then charge is going to be circulating. They are not showing the equivalency. The resonance structure 3 and 4 for the carboxylate ion are equivalent, more stable. Hence, carboxylate ion is relatively more resonance stabilized than the phenoxide ion. Thus, carboxylic acid is more acidic than phenol. So, yesterday I told you about the stability or acidic strength. Acidic strength, first one is a carboxylic acid, then carbonic acid, then phenol, then water, then alcohol. Alcohol are the least basic acidic character, then water, then phenol, then carbonic acid, and the first one, which is the strongest one, is a carboxylic acid. So dear students, this is the resonance structure and the stability of the carboxylic acid and acidity of carboxylic acid as well as the phenol. So reactivity we done, oxidation, nomenclature, comparing acidity, phenol and carboxylic acid. Then we direct go ethers. Article 18.3. Skip other. Ethers. Ethers. We are talking about the last topic, chapter number 18. And now, ethers. So ether's functional group is alkyl group, oxygen alkyl group. This is the functional group of ethers. There are symmetrical ethers and there are unsymmetrical ethers. So here, first one is a nomenclature. Nomenclature of the ether. So first one is, this is a dimethyl ether. Dimethyl ether, and you connect here, this connect here, methoxy, one carbon single bond methane, methoxymethane. Alphabetically, ethyl, methyl, ether. Connect always smaller number of carbon atoms. Methoxyethane. Methoxyethane. This is isopropyl methyl, or alphabetically methyl. This is a branch. Isopropyl methyl isopropyl ether, or 1 2 3 2 methoxy propane, 2-methoxy propane, or methyl isopropyl ether. So these are the symmetrical and unsymmetrical ethers here. Now IUPAC system, methoxyethane, methoxybutane also. You can increase the number of carbon atoms, then you can get butane here. Preparations. Now ethers can be prepared by two very important methods. One is called Williamson's method. Preparation. The first method is called Williamson method. So in this method, you use the alkyl halide with alkoxide. Alkyl halide with alkoxide. So alkoxide will be prepared. You can use ethoxy, methoxy. Suppose you are using methoxy, means methanol. You can use also ethoxy, means ethanol. Yes, here. So methanol reacts with sodium to give a methoxy. Sodium methoxy plus hydrogen gas. We are only concerning this. Same case for here. Sodium metal is going to react, so you will get ethoxy. Sodium ethoxy. Hydrogen gas is going to be like this one. So this is the sodium methoxy, and this is the sodium ethoxy. So then you have to combine with alkyl halide. So this is the CH3O, sodium methoxy, methyl chloride. They are going to be react. Sodium removed from here, chlorine removed from here, alkyl will be attached. So you will get dimethyl ether plus sodium chloride. In this case, sodium ethoxy plus ethyl or methyl, both ethyl chloride. So you will get another symmetrical ether, diethyl ether plus sodium chloride. So these methods are used for the preparation of symmetrical as well as unsymmetrical by using alkyl halide and alkoxide or methoxide. So this is number one method. Number two, second method is reaction with alkyl halide with silver oxide, dry silver oxide. This is the alkyl halide 2 two molecules of alkyl halides plus dry silver oxide. So you will get the ether and silver halide. So simple. Ethyl chloride plus ethyl chloride, silver oxide, dry. So you will get diethyl ether plus silver chloride. So this method is called reaction with the alkyl halides with the silver oxide. There are two methods. Second method is dehydration of alcohols. Dehydration of alcohols, please remember that conditions are very important. Dehydration of conditions are very important here. You have ethyl alcohol plus 2 moles ethyl alcohol, concentrated sulfuric acid. Conditions very important. 140 degrees centigrade. So you have to remove hydroxyl group and hydrogen from here. So you will get ether, diethyl ether and water. This is the third method. This is the ethanol and this is the ethanol, concentrated sulfuric acid, 140 degrees centigrade, hydroxyl group from here, hydrogen from here to make a water. One oxygen is there, they combine to give a diethyl ether. So this is another method for the calculation for this one. And you can use the unsymmetrical also, mixtures of ethers. Mixtures of ether you will get. So if you have 3 moles of ethanols plus methanol, 3 moles of ethanol and 1 mole of the methanol, heat it, and in the presence of sulfuric acid, so you will get the different mixtures. You will get diethyl ether, you will get diethyl ether and also dimethyl ether, diethyl ether and also unsymmetrical ethyl, methyl ether plus 3 water molecules. Different. There are 3 molecules of ethyl alcohol. So take 2 to make this one. Take 1 ethyl and 1 methyl here to make the ethyl ether and dimethyl ether also. This is there. These are the methods for the preparations of ethers. Ethers are very low boiling liquids, highly inflammable, and they are inactive during the chemical reactions. We use as a solvent. They dissolve fats, oil, gum, and many other organic compounds. Very good solvent we use as a solvent. And ethers are soluble in the concentrated sulfuric acid, characteristic oxygen containing compounds. This property is used to test for distribution between ethers and saturated hydrocarbons. Lower ethers acts as an anesthetic purpose. ethers are lighter than water. Chemical reactivity, you can see their image is given 208 page. You can see in between there the red. This shows a highly saturated of electrons are much more, the electron density is very high because oxygen is in between. There is a like this one. This is the image, dimethyl water maybe, like this. So this is a highly saturated, electron density is very high, red. So that's why this is given in the red. And outside, alkyl groups are attached here. The red is a high electron density, and blue area is lower electron density for this one. So ethyl oxygen is in between in the alkyl groups, and the high electron density due to the lone pair electrons towards the oxygen. Ethyl oxygen atoms act as the Lewis base because more electrons are here. Like the alcohol, OR group is poor leaving group and more attacking group, and needs to be converted to better leaving group before substitution occurs. It's more important of ethers of their cleavage of strong acids such as hydroiodide, hydroiodic acid, and hydrobromic acid. Ethers are resistant to attack unusual chemical oxidizing agents. Moreover, reagents like ammonia, sodium, alkali, and acids have no chemical reactions on other. That's why we call them, they are inert solvent. So there are only a few chemical reactions that are given here. Reactions are very limited. You can see this is the ether, and reaction with the hydrogen bromide. Oxygen atom of ether molecule possesses unshared electron pair, I have already here, which accepts the proton from the hydrogen bromide to give a oxonium ion. Sometimes they ask us write a formula of oxonium ion. So this is oxygen, this is the alcohol. So there is a hydrogen attack, positive charge is created. This is called oxonium ion. And bromide is going to be, this is a oxo. This is called oxonium ion. So, which accept electron, no further chemical reaction taking place. Only this you will get, no further chemical reaction taking place. But if you use iodine, if I am going to use iodine, hydroiodic acid, much more stronger acid than that of the hydrobromic acid. So first of all, you will get the oxonium ion. This is oxonium ion, and this oxonium ion is further react with the iodine. So one bond is going to be cleavage, this bond is going to be broken down, and you will get alcohol and plus alkyl iodide. So you can use the diethyl ether and the hydrogen iodide, then you will get ethyl alcohol and ethyl iodide. So dear students, this chapter is going to be end here. Solve all the exercise questions related to reduced syllabus and also MCQs according to the reduced syllabus. So there is the end of this chapter. Inshallah, we start chapter number 19. Next, aldehydes and ketones. So we end the chapter number 18. Thank you very much.